In this video, we're going to be talking about vector projections. So we have this vector u here, and its terminal point is on 2, 6, and we have this vector v, whose terminal end is on 5, 2. And when we talk about the projection of vector u onto vector v, what we're saying is this. We're looking at a dotted line that runs through the terminal point of u as well as v, and this dotted line is going to be perpendicular to vector v. And then when we look at the point of intersection between the dotted line and vector v, and we draw a vector whose initial point's on the origin and whose terminal point is at that intersection of this dotted line that goes through the terminal point of u and is orthogonal to v, that point will be the terminal point of this projection vector, and it's called the projection of vector u onto vector v. You'll also see this representation, the component or comp of u onto v, and you can see it's basically a vector in the direction of vector v, whose length is going to vary depending upon what vector you are projecting. So in this case, we're projecting vector u, and it looks like it's making v shorter in this case. But if we want to be very clear about the length of the projection vector, then how are we going to do that? Well, we can see that this vector here, and let's say we turn this into a vector, and let's say we call this vector here, this vector v perpendicular. So we can see the projection of u onto v perpendicular, and u form a right triangle. So if these three vectors form a right triangle, then you might expect that the length of this projection vector projection onto v of u is going to be the length of u times cosine of this angle, because this is the adjacent side here. Remember, cosine's adjacent over hypotenuse, so the length of this projection vector should be the length of u times cosine of the angle between u and v. But let's say we don't want to deal with sines, cosines, or thetas, and we just want some expression for the length of this projection vector in terms of u and v, and let's say we're allowed to use the dot product. Well, hopefully you remember that u dot v, one way of representing it is u1 v1 plus u2 v2. That's just the sum of the products of corresponding components of u and v. But another way to represent this is the magnitude of u times the magnitude of v times cosine of theta. And I've drawn single bars here, and these look like absolute values, but remember that these are vectors here. U and v are vectors. u1 and v1, u2, v2 are all scalars. But these look like absolute value signs, but they're actually magnitudes. If I really wanted to be precise in my symbolism, I would have put double lines on either side, but I just wanted to save myself some effort and didn't want to draw that extra line. So this is u dot v. So another way to represent cosine theta would be u dot v over magnitude of u times magnitude of v. And all I did here was divide both sides of this expression by, or this equation, by magnitude of u and magnitude of v. So if I wanted to represent the length of the projection of u onto v, then that would just be u dot v over magnitude of u times magnitude of v. This is the cosine theta part, and remember we multiply by the magnitude of u. So times the magnitude of u. These cancel, and we just get, should be an equal sign, u dot v over magnitude of v. So now just looking at this, we can figure out the length of this projection vector. Well, what is it? It's going to be u dot v. So that's going to be, so here, projection of u onto v. It's going to be u dot v over magnitude of v. So what's that? We're going to be multiplying the corresponding components of u and v and adding them to one another. So 2 times 5, that's u1 times v1 plus u2 times v2, so plus 6 times 2 over the magnitude of v. That's going to be the square root of 5 squared plus 2 squared. Looks like it's the square root of 29. So we have 22 over the square root of 29. So this is 22 over something a bit bigger than 5. So you can see the length is about, looks like it's about 4 something. And that looks about right from this picture, because the length of v is going to be square root of 29, which is a bit bigger than 5, and 4. This looks like it's, this projection vector looks like it's about 80% the length of vector v. So this is, this is about 4. But let's say we wanted to actually find out what this vector itself is, not just the length, but the actual vector. Hopefully you remember that any vector is equivalent to the unit vector in its direction times the length. So one way of writing vector v would be the magnitude of v times a unit vector in the direction of v, and it's going to be v over the magnitude of v. We've taken v and divided by its length to get a unit vector, a vector of length 1 in that direction. So we'll do the same thing here for this projection, for the projection of u onto v. The only thing is that we know, or I should say what you should keep in mind is we know that this projection vector is in the length of v, because we projected u onto v, so the resulting projection vector, it's in the direction of v. Did I say in the length of v? I meant direction of v. Sorry about that. So we have the magnitude, the projection of u onto v, times the direction vector for v. So what's this magnitude? Well, we have from here, it's u dot v over the magnitude of v. times v over the magnitude of v. So this is just going to be u dot v over the magnitude of v squared. Oops. I'll keep the single lines to keep it consistent. Times the vector v. Okay, so what does that help us do in this case? So let's say we're projecting this vector u2, 6 onto the vector v5, 2. So we can just go ahead and use this formulation here to figure out this actual projection vector. So u equals 2, 6, and v equals 5, 2. Oops. And here we're projecting u onto v. So, oops, projection onto v of u. That's going to equal, again, 2 times 5 plus 6 times 2. So 10 plus 12 is 22. Should be a 10 here. Magnitude of v squared is just going to be 5 squared plus 2 squared. It's 29 square root, but then we square that, so we just have 29. Then we multiply by v. Well, what was vector v? It's just the vector 5, 2. So we have 22 over 29 times 5, 2. And really what you can see here is that the projection, determining this projection vector really amounts to determining a scale factor for v, like the length of this projection vector relative to the length of v. You can see we get some number here multiplied by v. So we're going to get a vector in the direction of v, but that's going to be 22 over 29 times the length of v. So that's really all there is to projections. In another video, I'm going to go over how we got this formula here. Remember, we made a substitution for cosine theta that involved the dot product, and that came out of the fact that u dot v can be represented as the magnitude of u times the magnitude of v times cosine of theta. But remember, the definition of u dot v is really u1 v1 plus u2 v2. So why does this definition lead to this formulation of the dot product? And that's something I'm going to cover in another video.